Hello students, in the last class we discussed about the two topics. Now we are in the discussion of topic 3. That means earlier we have learnt about irrational numbers and their properties. In this topic we shall prove that root p, where p is a prime number, are irrational numbers by using the following theorem. What is that theorem? See, here we can understand. If p is a prime number, p divides a square, then p divides a, where a is a positive integer. If p is a prime number, then root p is irrational. So, in the topic 3, we are discussing about revisiting irrational number. What do you mean by revisiting irrational number? So, to understand this revisiting irrational number, we have to understand this theorem statement. If p is a prime number, p divides a square, then p divides a, where a is a positive integer. If p is a prime number, then root p is irrational. So to understand this theorem concept, we have to solve based on this topic some problems. Then you will understand very easily. Let's solve the problems. Okay, now we can understand. Here they given one problem. Prove that root 5 is irrational number. So we have to prove that root 5 is a irrational number. So we know that we have to prove that irrational number. First let us assume let root 5 is equal to p by q. So it is in the form of p by q. Be a rational number where p and q are co-primes when q does not equal to 0. So we have to prove root 5 is a irrational number, but we have to assume first root 5 is what? Is a rational number. So root 5 is equal to p by q, be a rational number where p and q are co-primes and q does not equal to 0. Then what happens? Then root 5 is equal to p by q. We can write rational number can be written in the form of p by q. So root 5 into, so on transposition. So what happens? Then root 5 into q is equal to p. And squaring on both sides, then root to square root gets cancelled. Root 5 will become 5. Q will become q square. It will become p square. Then p square is equal to 5q square. Since if 5 divides p square, so it will be divide p also. Let p is equal to 5r. Then p square is equal to 25r square. What we did here? We did here squaring on both sides. But we know the value p square is equal to 5q square. Substitute this value in this place. Then you will get, in the place of p square, we can write, this is called it as 1. From 1, write the value of p square. The value of p square is 5q square, that is equal to 25r square. 5 gets cancelled. Q square is equal to 5r square. So we can say that since 5 divides q square, so it will be divide q also. Thus 5 is a common factor of both p and q. This contradicts our assumption that root 5 is a rational number. So root 5 is a rational number, which implies hence root 5 is a irrational number. Have you understood, student? Let's solve one more problem based on this. Okay, students, let's take the same type problems, just we have to change the numbers. Prove that root 2 is irrational number. We have to prove that root 2 is irrational number. So to prove, before proving that, let us assume that root 2 is a rational number. If root 2 is a rational number, what do you mean by rational number? A number that can be expressed in the form of p by q. So we can find the integers of a and b where b does not equal to 0, and we know that a, b are co-prime numbers. Root 2 is a rational number. That number can be expressed in the form of p by q. Either you can write p by q also, a by b also, m by n. Any integers you can take. Root 2 is equal to a by b. So on cross multiplication, so root 2 into b, root b is equal to a. Squaring on both sides. Squaring on both sides, if you square on both sides, squaring on both sides, 2b square is equal to a square. Therefore, 2 divides a square, which implies 2 divides a. 2 divides a square, which implies 2 divides a. A can be written as 2m where m is an integer. So here we can write a value 2m in equation 1. Replace the value of a by the value of 2m. What happens? The equation 1 gets changes. 2b square is equal to, in the place of a, we can write 2m. But it has 2a square. It will become 2m whole square. 2b square is equal to 2 square means 4. M square means m whole square means m square. 2 ones are 2 twos are. What will be left here? B square is equal to 2m square. 2 divides b square, which implies 2 divides b also. So like this we can prove that. What we can give the contradiction at the end of this? So we can say that 2 is a factor of a and b, which contradicts that a and b are co-prime number. Therefore, our assumption is true. Hence, we can say that root 2 is a irrational number. Understood, student? Okay, let's take one more problem. You can understand this theorem. So like that we can take one more problem. Prove that 5 root 2 is an irrational number. How to prove this problem? Here we can, the same steps here, the steps will be common for proving all the problems. First, what we have to assume? We have to assume that 5 root 2 is a rational number. Then, if it is a rational number, then we know that p by q is an integer where p does not equal to 0 and a, b are co-prime numbers. The common steps you have to write each problem before proving any problems. Okay, then what we are doing? Let us assume what is the given number? 5 into root 2. Let us assume 5 by root 2 is equal to a by b. Why? Because we are assuming, what we are assuming, 5 by root 2 is a rational number. If it is a rational number, we have to express that is in the form of p by q form. Then on cross multiplication, 5 into root 2 into b is equal to a. You have to prove 5 into root 2 is a rational number. I am keeping root 2 on LHS side. Root 2 is equal to a by 5b, which is a rational number, which contradicts that root 2 is a, which implies that root 2 is a rational number, but this contradicts that root 2 is a rational number. So 5 by root 2 irrational number. Okay, student, have you understood? Shall I explain once again? First step, let us assume that 5 into root 2 is a rational number. Then we can find a and b. Where b does not equal to 0, a and b are co-prime numbers. 5 root 2. If it is a rational number, we have to write in the form of a by b form. 5 into root 2 into b is equal to a. Root 2, if you want, a by 5b, which is a rational number, which implies that root 2 is rational, but this contradicts the fact that root 2 is irrational. So 5 into root 2 is irrational. We have to take one more example to understand like this problem. So here let us take one more problem. Prove that root 2 plus root 3 is irrational. How to prove root 2 plus root 3 is irrational? Same thing, let us assume that root 2 plus root 3 is rational number. If it is a rational number, where a and b we can express in the form of p by q or a by b, where b does not equal to, here I am taking a numbers integers a and b, their co-prime number, b does not equal to 0. Then root 2 plus root 3 is equal to a by b, root 3 is equal to a by b. I am shifting root 2 to LRHS, then it will become minus root 2. Squaring on both sides, what we are doing? Squaring on both sides. If you square on both sides, what you will get? Root 3 will become 3. 3 is equal to a by b minus root 2 whole square. What happens here? Now it is in the form of a minus b whole square. A minus b whole square means what? A square plus b square minus 2ab. Use that identity and expand. So on squaring on both sides, root 3 square root to square root gets cancelled. A by b minus root 2 whole square. So it is in the form of a minus b whole square. Use that identity and simplify. A by a by b minus root 2 whole square is equal to 3. Then we apply the identity a square plus b square minus 2ab. Then what happens? So your plus 2 and plus 3 is there. I am shifting root 2 plus 2 to RHS. Then what happens? It will become minus 2. So 3 plus 2, 3 minus 2, it will become 1. A square by b square. What will be left at the LHS? RHS 2a by b into root 2. Then finding the LHS for the denominator, a square minus b square by b square is equal to 2a. 2a into root 2 by b. B square is square, one b and another b will be gets cancelled. What will be left at the remainder? A square minus b square by b is equal to 2a into root 2. On cross multiplication, keep the root 2 or RHS only. A square minus b square, this 2a comes to denominator 2ab. But we know that a square minus b square by 2ab is a rational number. If it is a rational number, which implies that root 2 is a irrational number. Hence, we have to prove that root 2 plus root 3 is a irrational number. Hence, our assumption is we have to prove root 2 plus root 3 is irrational. That's all, students. Let's go to the next concept. Okay, student, the next concept, revisiting the fourth topic, revisiting rational number and their decimal expansion. Okay, so in your previous class, we have learned that all rational numbers have either a terminating decimal or non-terminating repeating decimal representation. Is it true, student? So we know that in your last classes, now we are discussing revisiting rational number and their decimal expansion numbers. Rational numbers that can be either terminating. Is it right? Rational numbers can be expressed. There are two types of either terminating decimal number or non-terminating recurring. Recurring means repeating number. So let's see one by one in this session. See, student, in this topic we will consider a rational number, say p by q or m by n, any number, and explore exactly when the decimal expansion is terminating and non-terminating without actually performing long division process. That means we have to understand a number which cannot be expressed in the form m by n, or we can take a by b, or we can take p by q, where m and n are integers, q does not equal to 0, is called irrational number. Decimal expansion of a rational number is either terminating or non-terminating but repeating. So we have to understand very most important basic terms in this topic 4. That means a number that cannot be expressed in the form m by n, where m and n are integers, q does not equal to 0, is called irrational number. Decimal expansion of a rational number is either terminating or non-terminating or non-recurring. Is nothing but recurring. Terminating, recurring means repeating. We have to keep these 2 points in your mind. So based on this, some 3 sub points are there, some small theorems on this concept. Let's discuss one by one. Okay, students. See here some important theorems regarding this. We have small 3 theorems. Theorem 1. Let us assume, x be a rational number whose decimal expansion terminates. Terminates means the division process, it will be ends. Let x be a rational number whose decimal expansion, the decimal expansion terminates. Then x can be expressed in the form p by q. That means we have to express this number as a rational number where P and Q are co-prime numbers and the prime factorization of Q, that is in the form of 2 power m into 5 to the power n, where m and n are non-negative integers. I'll repeat again. What is this theorem meaning? The meaning of this theorem is nothing but, let us assume that, let x be a rational number. If they given any rational number, if you want to find whose decimal expansion is terminates, if the decimal expansion is terminates, then we have to express that number in the form of P by Q, and that P by Q, know that always that's a prime factor, co-prime number, and that prime factorization of Q that can be expressed in the form of 2 to the power m into 5 to the power n, where m and n are non-negative integers. To understand this, we can take some examples. Through this example, we can understand this theorem 1. That means 0.25 that can be written as, this is the decimal expansion. We can write in the form of decimal expansion. So it can be written as fraction form P by Q, that means 25 by 100. 25 by 100 it can be written as 25 ones are 25 fours are, we'll get the 1 by 4. Again, if you want to write that prime factorization, that is in the form of 2 power m into 5 power n, 4 can be written as 2 to the power 2. Is it right? But 5 power n, it does not have any number, that's why you have to write 0. It can be written as 1 by 2 power 2 into 5 to the power 0. So you can take another example. These all are decimal expansion, decimal expansion of terminating numbers. So 0.73773, that can also written as 700, and after decimal place 3 points are there, 3 digits are there. So you have to express 773 by 1000. 773 by, so if you find out the prime factors of 1000, you will get that. What are the factors of 1000 means 2 into prime factors, 2 into 2 into 2 into 5 into 5 into 5. Then you will get, it can be expressed as 773 into 2 power 3 into 5 power 3. Now it all in the form of 2 power m into 5 power n. This is known as theorem 1. Have you understood, children? This is the very most important concept. Okay, students, the next thing will be theorem 2. This is nothing but converse of theorem 1. What we learned? The first theorem whose converse only. That means it will be a reverse. If a rational number x is of the form P by Q such that prime factorization of Q is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integer, then x has a terminal decimal expansion. You have to remember once again in the theorem 1 what we said. If x has a terminating decimal expansion, then it will be expressed in the form of 2 power m into 5 power n. Converse means it will be a reverse. What will be reverse? A rational number is of the form 2 power m into 5 power n. Then we can say that this x has a terminating decimal expansion. Reverse only. So we can see this example. 7 by 8 can be written as 7 by prime factorization of 8 will be 2 power 3. There is no power of 5. Then we can written as 0. So this will be equal to P by 2 to the power m into 5 power n, where m is equal to 3, n is equal to 0, P is equal to 7. Then we can say that 7 by 8 as a terminating decimal expansion. It's a very easy theorem. We all understand. Once again we have to read all these theorems carefully. It's a very easy chapter. We have to understand the theorem correctly. Like this, another last theorem 3. Same only. Let x be P by Q is a rational number such that the prime factorization of Q is not of the form 2 to the power m into 5 to the power n. Have you understood, children? Shall I repeat again? Okay, students, this will be a very last important concept of your chapter, real number. The same thing only. If x is equal to P by Q, be a rational number such that the prime factorization of q is of the form 2 to the power m and 5 to the power n, where m and n are non-negative integers. Then x has a decimal expansion which is in the form of terminating decimal, terminating, repeating. You have to understand correctly. So let x is equal to p by q be a rational number such that the prime factorization of a q is not of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. Then x has a decimal expansion. What is the decimal expansion? In this theorem 3 explains the decimal expansion of the form non-terminating, repeating, that means recurring. You should see an example, 19 by 35. It can be written as 35 can be written as prime factorization 5 sevens are. The denominators, that is in the form of 2 to the power m into 5 to the power n. So where m and n are the non-negative integers. Therefore, we can say that 19 by 35 has a non-terminating, repeating decimal expansion. This is the very most important concept of in this chapter, real number. Totally, whatever the points we have to learn in this chapter, concepts of factor 3 and theorems, HCF, LCM using prime factorization, we discussed in this chapter. So Euclid's division algorithm, lemma, everything. Once again you have to revise all the concepts. Lemma means a lemma is a proven statement used for proving another statement. Algorithm, an algorithm is a series of well-defined steps which gives a procedure for solving a problem. Next concepts, Euclid's division lemma. In a given positive integer, there exists a unit integer such that a is equal to bq plus r. And also we learned the method of proving irrationality of numbers. Topic 3, that means revisiting irrational numbers, and topic 4, revisiting rational numbers and their decimal expansions. Is it right? So topic 3, revisiting. What are that topics? In that we learn 3 theorems. Is it right? Topic 4, revisiting rational numbers and their decimal expansion. What is the theorem 1 says that when x be a rational number whose decimal expansion terminates, then x can be expressed in the form of p by q, where p and q are co-prime and the prime factorization of q is of the form 2 to the power m into 5 to the power n, where m and n are non-negative integers. Theorem 2 says that if a rational number x is of the form p by q such that prime factorization of q is of the form 2 power m into 5 power n, where m and n are non-negative integers. Theorem 3 says that x is equal to p by q be a rational number such that prime factorization of q is not of the form 2 power m into 5 power n, where m and n are non-negative integers. Then x has a decimal expansion. So methods to write the decimal expansion of those rational numbers which have a terminating decimal expansion and non-terminating decimal expansion. Is it right, children? Based on this, we have to solve the problems. Some examples we already given. So you have to solve exercise problems, work out the exercise problems. Very most important in this unit, they will ask to prove the here they are asked to prove that Euclid's division lemma, Euclid's division algorithm, and they are asked to find root 2 is a rational number, root 3 is a rational number, root 2 plus root 3 is a rational number. Like that they are asked to find out.